Okay, for the last objective in Module 2 is learning how to actually go out and collect the data. So now we're really getting into data capture. So the objective of this is to describe different data capture techniques. And so really, when I say data capture, what does it really mean? It means to go out and get data, right? So there's more than one way of doing that, of course. So because of the different types of files and the different types of data, we have to use different ways to be able to get that data. So there are two main types of data collection. The first one is a primary data capture, which is where you go out and actually collect it in some sort of digital format. And it's specific for you, it says specifically for use in a GIS, but it doesn't necessarily have to be because it can be from other methods as well. But if you go out and collect it to bring it and to use it for the project, then it can be considered primary. Where there's secondary data capture, and this is where you either have an analog or a digital format, and it's really something that has been captured for a different reason, and it is bringing in it's bringing that in to the GIS in some sort of usable format. So a couple examples of primary sources is remotely sensed data, so satellite or LiDAR. You can also use GPS, which you can use mapping or survey grade for that. Or you can do land surveying itself and the field observations that come with that. So those are kind of the main primary sources. Or you go out and do a survey, for example, you're not just land surveying, but you go out and survey people if you're doing something in like the human geography or demographics, for example. The other one is secondary sources, which is you can use tables that have XY coordinates. You can go online and download it. You can do digitizing. And so there's different ways to do digitizing. And there's also scanning, which is known as vectorization. And there are some automated methods for that. Some are better than others, but of course, cost comes with it too. So prior to going out and collecting your data, you need to know that what you are actually going to do, right? So you need to be very clear. You need to have a scope. You need to know exactly what you need to collect because the world is really hard to generalize because there's a lot of information that you can collect. So there is a lot of upfront work that needs to be done, and then it's ongoing. So as the project develops, you might see you missed something, you got to go back and get it, or maybe something isn't enough, so you need to go get more. So this is definitely a big upfront start, and then you have to keep maintaining it. So we use a bit of a data capture rule. It's actually very similar to something called machine learning. So if you've used that before. So in data capture, you need to have an 80-20 rule where 80% of the data is dedicated to capturing and managing the project, where 20% is actually analyzing. So in machine learning, 80% is to develop it and create it, and then 20% is to test it, right? So the same idea here. And so a GIS is really only as good as the data you put into it. Garbage in, garbage out. That's what you end up with. So some considerations we need to worry about. The first one is accuracy. Again, your client should let you know what accuracy they require before you even go out. Currency as well. Accuracy comes with cost. So the higher accuracy, the more money it's going to cost. And then, so there's that. You can also think of currency because there's budget below there. You can also think of currency as how soon the data has been taken. So for example, if I'm making a map for 2022, and we haven't done a census since 2019 or 2018, it's not going to be very up to date if I'm going to be doing a lot of demographic stuff with the census data. Also, existing data availability. Sometimes if you can't get that data because it's not available, you have to go get it yourself. But sometimes it's available, and then that saves you a lot of time and money to be able to access that data if you're able to. Also, the urgency of acquisition. So again, how fast does this GIS system need to be developed? There's also the data structures. So again, what kind of data do I need to collect? Because I have to keep in mind what kind of symbols I'm going to use and how I'm going to actually visualize it. Budget, I've already talked about that. And then a joint venture possibilities. So is there a possibility to use that data for other options, and then it'll help save on cost and even time. So one of the methods of data capture is surveying. So survey data has traditionally been the most accurate, and this particular surveying that it's talking about is land surveying, not just going out with a form and asking people questions. So it is really the most accurate way. You have to go out and actually manually measure the locations, so you get lengths and angles. If you use real land surveying equipment, then you know that you can trust your answers if you know what you're doing. And getting those lengths and angles will really give you a good measurement as to where you're located. There's something called a bearing. This is an angle where you can set a arbitrary 0, and then you can create an angle based on like that arbitrary 0, or you can set it based on an azimuth. So a bearing is between 0 and 90 degrees. It's not necessarily anything past that if you use a quadrant bearing. There's other bearings which are allowed to be greater than that as long as it's within 360 degrees. Again, if you really want to get into surveying, I suggest going and taking a geomatics program, because then you'll really get that accurate data and you'll be able to use the equipment, and you'll be able to understand what the data they're giving you and what it means when you get an accurate bearing or an accurate quadrant bearing or an accurate azimuth. So that would be a geomatics program that you would do for that. Also, there is the distance, of course, the distance between two stations or two objects. A course is the direction that you are going through the actual survey. You can also talk about a traverse, which is like a line as we go through. So again, a lot of this terminology that you're seeing here is land surveying terminology. And if you want to use that stuff, make sure you're trained on it in a proper program, because otherwise there is a high possibility of error. So survey data is used in construction and parcel measurements, so it does have extremely high accuracy. You can get like millimeter level for sure. Sometimes if you really need high precision surveys, you might get sub-millimeter level for accuracy. Again, there's a lot of money that goes into that if you're going to do it. So it's like a deformation survey where you're watching something, just making sure that something doesn't move. That can become very expensive. There is survey grade GPS, and the GIS world, it says it's starting to be adopted in this discipline. It has always been in there. It's just that because it was so expensive that people would just use it in like engineering plans and like plans for the ground for your parcels. You would get subdivision plans and stuff. So that was usually what it was used for. And GPS has been around for a while. But the survey grade GPS is because if you need a high accuracy GPS, you can definitely use it for this to be able to create control points. It's expensive, and again, make sure you know what you're doing with that, and I would suggest doing a geomatics program if you're going to use a survey grade GPS, so that you know what errors are expected and what it means when you are working with that data. Then there's coordinate geometry, which we call COGO in the world of geomatics, and it's a way of storing survey data as geospatial data. It's actually a way to calculate coordinates, is what it is. And it does all the calculations within that. So if I need to do an intersection, I can do it with the COGO. For the most part, it's a downloadable program onto your calculator that you would use, or it would be found in some sort of data collector that you would hook up to your system. Again, all of this stuff, if you do want to use it, I strongly suggest taking a geomatics program so that you have the ability to use the equipment without error. So GPS is getting to be more and more common, but there's also the case of it, because it's more common, it's becoming misused. So if you're using a survey quality GPS, again, that is a highly accurate system, and you're easily going to be paying $80,000 for a really good system. Some systems are about 25,000. Again, not as accurate, but you can get like you can get an okay quality. But we also have that in our phones. So for the most part, the quality that you have in either like a handheld GPS or like a mapping quality GPS or your cell phones generally is good enough for a lot of the thematic stuff that you would be doing. So, so if you're going to be using one of the like a handheld GPS, there's a few things you need to watch for while you're collecting data. So first of all, GPSs use satellites. They don't use cell phone towers and all that. They actually use satellites, and they use something called trilateration. It says triangulation. It's not using triangulation. It uses trilateration, and that's a three-dimensional like sphere in order to figure out where you are located. Then the GPS device receives the satellite signals, and then it interprets the time that it took between the satellite and the actual system, because it sends a code. It says, "Hey, the satellite says I sent this code at this time," and then it comes down to your receiver, and it says, "Okay, I've received it at this time," and then it's got to figure out what is in between. Now, part of this is that I'm only going to be receiving some of that code, and I have two different clocks. So it's not just looking at the speed and time. And it will receive it, and we have something called a float versus a fixed position. And so handheld GPSs, if it's bouncing around, it's in a float position. If it seems to be stabilized and just moving a little bit, then it is in a fixed position. To get that's because we have something called ambiguity. So again, that's a whole other class in GPS on actually how to use a GPS properly. But a handheld GPS, you don't have to worry too much about it, because the accuracies are low anyways, so it's not the end of the world if it's kind of off. You really need a fourth satellite. It says a minimum of 3. Sure, you can use a minimum of 3 to get X, Y, and Z, but you really need that fourth satellite in order to get the timing errors, because even a 1 second error is like a 3,000 kilometer error on the ground. So 1 second is like 3,000 kilometers. So if you don't have that fourth satellite, you're only really accurate within 3,000 kilometers. So that's you really need that fourth satellite to be able to get that. Now, for the most part, you will pretty much always have 4 satellites unless you are under a canopy, and then you need a special system for that. So the old GPS system, and I guess the original system, is known as Navstar. We don't really call it Navstar, it's just GPS now. But there is GNSS, which is the Global Navigation Satellite System, which is where you might have GLONASS and Galileo and Baidu, which is coming up soon. And all of those can be combined into one. So it's not just GPS anymore, it's GNSS. You might have to pay for licenses of the different systems, but it is, you have all these nice systems that you can use to be able to get accuracy. So there are 32 satellites in GPS. There's been 32 for over a decade. And you generally can see 5 to 8 of them, usually 10 at any time. If you are up north, for example, you're going to have fewer satellites just because of the angle. The higher you go north, the less reliable GPS is. That's where you need to use the GNSS system, which is the Global Navigation Satellite System, because you're using world data rather than just GPS. And it's just because GPS is at a 55-degree inclination angle. So now that I've criticized all the GPS and land surveying stuff there, honestly, the handheld GPSs are fine for everything that you guys will have to do, especially in this class. If you're trying to fly up the drone or something, you might need something a little bit more high end on that. But so another type of data capture is digitizing. So this is converting analog data to digital data. So there's 2 types of methods. There's a heads down method, or there's a heads up method. So there is the possibility to use like a tablet or like a digitizing table. I haven't seen them in a long time, but but they I guess they still exist, because most of it can be done with a mouse now. But it has like this special like platform that you can put a map down and you can like draw on the map, like you can draw the lines on the map, and usually it's like some sort of mouse or like a puck or something that you kind of draw on there. So it's not like a see-through thing that you're trying to redraw the map. But it's a tablet that can detect where that mouse is. The heads up is on the screen. This is what you will most likely be doing at some point in your life. In this career, we all do it. And so you have geo-referenced ortho photos. You can have satellite images, which are also geo-referenced. You can have scanned images. And what you're doing is just using your mouse and drawing on the screen. So it is a very manual process. Pretty much when you first start out in GIS, you're going to digitize. That's pretty much what you're going to do. It's not the most amazing job, but it is one that you end up doing. There are some accuracy considerations with it. So if you manage to get all the features and they were only digitized once and weren't accidentally done a couple times, how close you followed the features and those lines. Also, if you have intersecting features, like do they intersect at the right spot, and how many points were used in representing lines and polygons. So if you overdo it, you can like oversample or undersample. If you're trying to get high accuracy, you're gonna have a lot of points along a line, and that just takes more time. So pretty much every GIS package has a built-in digitizing module of some sort, so you can get that data. Another type of data capture is scanning. So you can take a map and you can scan an analog map into a file, and it becomes a vector format through tracing if you have the software. Otherwise, it might be saved as like a JPEG or a TIFF or a PDF. Well, PDFs are technically vectors, but it could be also saved as a vector or like SVG, something like that. So there are tracing algorithms within GIS packages. The accuracy of that depends on what you're scanning, and it depends on the algorithm. So they're getting better. It's becoming easier to scan them in and have them ready as different features, but the automated version of it is still it's still not great. So you definitely need some manual interaction with it. So some of these problems that the reason why automation is not perfect is how do you trace an intersection? Maybe there's a raster line that could be double or triple the width of what it actually is. So how do you draw that? And then how do you continue a broken line when you scan it in? It's like, because all of a sudden there might be a missing spot. Maybe it's just a really worn out map, or there's something spilled on it or something. So how do I do that? Or what happens if I have two lines that are really close together? When I scan it in, can the algorithm identify those as two separate objects, or is it just one? And then the other one is when I classify that data automatically, is a line a polygon if it goes around? Like, so for example, if I have streets and and they're all gridded, is it a polygon that I'm drawing, or is it lines that I'm drawing? So that's another one that's a little tricky. So some more data capture is remote sensing. So remote sense data, it can be acquired by all kinds of different platforms. So you can go on satellites or planes, drones, helicopters, trucks, balloons, tripods. It can be like on anything, really. So there's different types. There's satellite imagery, there's aerial photography, LiDAR. It says radar sat, that is a satellite. It's just a microwave satellite. So satellite imagery is becoming really popular because a lot of it becomes free because it's government funded, but a lot of it is also commercialized because they are trying to increase accuracy, or not accuracy, the resolution of it. So it's becoming more and more used just because it's more available. It's less, it costs less, the technology is costing less. We have better resolution, so it's becoming a little bit easier to map with, and the digital processing of it as well is also, like, the computers themselves are becoming more powerful, but we have a lot more semi-automated automated functions that you can go in and you can create an automatic classification of the data, and where historically it may have taken a lot longer and a lot of time. And a lot of those new semi-automated fashioned algorithms can include things such as machine learning and deep learning. And those algorithms are becoming really powerful in remote sensing. So we also have a lot more satellites out, so more data, more satellites, we can get more, be more timely. If you get some of the commercial ones, you can have like your own private satellite that follows you around almost. It's kind of, it doesn't quite do that, but it has an orbit. But yeah, you can have your own satellite that you can program. Then there's aerial photography. So there's analog and digital, of course. Most of it's digital nowadays, but you can still have some old stuff that you may need. It can be unreferenced or it can be referenced. So it depends on the system that was on board. And like for example, drones might have they might have a GPS unit on it, or they may not. And just so you can get that data, you might have to use targets on the ground that are geo-referenced, and then you have to geo-reference them yourself, so forth. You can use different kinds of aerial photography. So there's color, black and white. There's false color, infrared. You can go into more detail about that as well. And then we have different perspectives as well. So there's vertical, which is like where I'm looking straight down. And then there's also street view, which is where I'm standing on the ground looking towards a building. Or there's an oblique, which is where I'm in the air, but it's at an angle. So I can either have a low angle or a high angle. So there's different perspectives for sure. So here's an example of a vertical perspective. So you can see it looks straight down, and we don't really get a sense of elevation. I can also have street view, so now I can really see elevation right at eye level, but I have a very limited view of the area. And then there's oblique. So the weird thing about oblique is that you end up with scale issues because of it, but it gives you more of a sense of elevation. So a low oblique, you can't see the horizon, but the high oblique you can. But again, you don't want to use a scale on that, but it will allow you to maybe validate your data, or you can use it to put in some other classification information or attribute data. So in summary, you need to consider the best approach for capturing this data. As you can see, there's many kinds of data, and some require different kinds of training. Like a good example is drones. You need a pilot's license to do that, like a drone pilot's license. Then you have to determine what data model you want to use. Do I want to use a raster, or do I want to use a vector? And again, planning is the most important thing for that. And then finally, GIS is really only as good as the data you put into it. So garbage in, garbage out. And there's also the 80-20 rule, where most of your time is spent collecting data and 20% is actually analysis. So again, same readings, because we're saying in the same module. Now you can complete assignment 1. So you should have all the data you need. And here's some of the references, and that is the end. So I will be back for the next module next week.